Welcome to Quietly Made. I am so glad you have found your way here tonight. This is a space for the curious and the weary, a place where we explore the vast, invisible infrastructures of our world, while giving your mind the permission it needs to simply rest. Before we begin, I invite you to join our community by subscribing and leaving a comment. I often wonder where these stories find you tonight. If you feel inclined, please leave a comment sharing what part of the world you are in and the hour you are settling into sleep. It is a small way for us to feel the quiet connection of this community, scattered across different time zones, but sharing this same moment of rest. If you fall asleep, that is exactly what should happen. You are safe here. You can always come back tomorrow and pick up exactly where you left off. Adjust your pillow. Take a deep, slow breath in and let it out. Let your mind drift as we begin. Before we could teach sand to think, we first had to learn what thinking meant in material form. The human desire to calculate predates written language. Fingers served as the first abacus, 10 digits that could track livestock, measure grain, count the passage of moons. But fingers forget. They tire. They disappear when their owner does. What we needed was something that could hold a number even after the hand that made it had turned to dust. The earliest counting tools were stones pressed into wet clay, each depression representing a quantity. A shepherd could record his flock by pushing pebbles into a tablet, creating a physical memory that would harden under the sun. These weren't symbols yet, just honest representations. One stone, one sheep. The clay dried. The count remained. This was humanity's first act of storing information outside the mind. The first time we made matter remember on our behalf. In the markets of ancient river valleys, merchants needed to track exchanges that grew too complex for mental arithmetic. Goods moved between strangers who spoke different languages, who worshipped different gods, who trusted nothing but the weight of metal and the marks on clay. The need wasn't philosophical. It was immediate and practical. A trader who miscounted went hungry. A tax collector who lost track faced consequences from kings who did not forgive arithmetic errors. The counting boards came next, surfaces marked with lines where stones or shells could slide along grooves. Each position held meaning. Units here, tens there, hundreds beyond. Moving a stone from one channel to another represented addition. Removing one meant subtraction. The board itself knew nothing, but it allowed the human mind to offload the burden of holding every number simultaneously. The calculation happened in the space between hand and surface, in the deliberate movement of objects across wood worn smooth by countless transactions. These tools worked because they made the abstract concrete. 7 became 7 beads. 12 became a specific arrangement of counters. The physical world was being recruited to perform the work of pure thought. Matter shaped into the servant of mathematics. But every system had limits. The boards could only hold so many positions. The clay tablets could only record what someone remembered to press into them. Each tool was an extension of human memory, but still dependent on human attention. As civilizations grew, so did the complexity of what needed counting. Astronomical observations required tracking cycles within cycles. Architecture demanded calculations that involved fractions, angles, proportions that couldn't be easily represented with whole stones on simple boards. The gap between what we needed to calculate and what our tools could hold began to widen. We stood at the edge of mathematical problems that exceeded our ability to solve them manually, staring into a fog of numbers too vast to navigate with fingers and beads alone. The need that drove us towards silicon was already present in these ancient frustrations. We wanted to think bigger thoughts than our biology allowed. We wanted to remember longer than our lifespan permitted. We wanted to calculate faster than our hands could move. The sand hadn't learned to think yet, but we had already begun imagining what we would ask it to do once we discovered how to wake it up. The human brain, for all its remarkable capacity, functions as a serial processor when it comes to conscious arithmetic. We can hold perhaps 7 distinct pieces of information in working memory at once, a limitation that becomes painfully obvious when trying to multiply 3-digit numbers without external aids. Each step must be completed before the next can begin. Each intermediate result must be carefully maintained while the next operation proceeds. One moment of distraction, one wandering thought, and the entire calculation collapses like a tower of carefully stacked coins scattered by a sudden breeze. This biological bottleneck became more apparent as mathematics itself evolved. The development of algebra introduced variables, placeholders that could represent unknown quantities. Suddenly, problems weren't just about counting actual things, but about manipulating abstract relationships between numbers that might not even be specified yet. The mental juggling act grew more demanding. Paper became essential, not just for recording results, but for extending the mind's workspace. The margins of manuscripts filled with scratchwork, intermediate steps, the debris of thinking made visible. By the time calculus emerged, the gap between human capability and mathematical ambition had become a chasm. Calculating the trajectory of a projectile required integrating functions, solving differential equations, managing multiple variables simultaneously across iterative steps. A single ballistics problem could consume hours of careful work, and a single misplaced decimal point would render all that effort worse than useless. It would produce a confident answer that was precisely wrong. The military applications made this limitation dangerous. Artillery needed accurate firing tables. Naval navigation required precise astronomical calculations. A ship's position at sea depended on comparing observed stellar positions with predicted values, computations that demanded both speed and accuracy. Lives hung on mathematics performed by tired human computers. Yes, that was the job title. People, usually women, who sat in rooms filled with mechanical calculators and performed the same operations over and over, checking and rechecking, knowing that errors would be measured in capsized vessels and misdirected shells. Industry faced similar constraints. Engineering a bridge required calculating load distributions, stress factors, material properties across hundreds of individual components. An error in the foundation calculations might not reveal itself until the structure failed. Insurance companies needed to process actuarial tables, computing risk across thousands of policies. The telephone system, as it grew, demanded switching calculations that scaled exponentially with each new subscriber. The mental effort required to manage these expanding systems grew faster than the human population able to perform it. What we needed was impossible by the standards of biology, a thinking process that never tired, never lost its place, never rounded incorrectly or transposed digits. We needed something that could hold 1,000 intermediate results without strain, that could repeat the same operation 1,000,000 times without boredom introducing error. We needed accuracy that didn't degrade over time, speed that didn't depend on whether the calculator had slept well the night before. The sand in the desert knew nothing of these frustrations. It sat in dunes, shaped by wind, in beaches polished by waves, in riverbeds filtered through centuries. Silicon dioxide, stable and inert, waiting without knowing it was waiting. The distance between that sand and the thinking machines we needed seemed infinite, separated not just by technical challenges, but by the fundamental nature of what matter could do. Sand couldn't think. Everyone knew that. Except eventually, we would prove everyone wrong. The first machines that could be called calculators emerged not from scientific laboratories, but from the same impulse that created music boxes and clockwork automata. If gears could be arranged to play a melody, perhaps they could also be arranged to add numbers. The logic was mechanical before it was mathematical. A wheel with 10 teeth, advanced by 1 tooth for each unit counted, would complete a full rotation at 10 and need to carry that value to the next position. This was addition rendered in brass and wood, thought translated into the language of engaged teeth and rotating spindles. These early mechanisms occupied the uncertain space between tool and machine. A lever amplifies force, but requires continuous human input. A water wheel converts motion, but must be fed by flowing water. The calculating machines of the 17th and 18th centuries operated similarly, transforming human effort into numerical results, but remaining fundamentally passive without an operator. You turned the crank, the gears meshed. Numbers appeared in small windows behind which painted drums rotated, displaying digits one at a time as the mechanism settled into its answer. The clever part was the carrying mechanism, the way a gear completing its rotation would nudge its neighbor forward by 1 position. This mimicked the human practice of carrying digits during addition, but executed it with the reliability of metal parts fitted together with precision. When the ones place advanced from 9 to 0, the tens place would automatically increment. The machine didn't understand what it was doing any more than a door hinge understands opening and closing, but it performed the operation correctly every time, immune to distraction or fatigue. Building these devices required the skills of watchmakers, artisans who worked in tolerances measured in fractions of a millimeter. Each gear had to be cut with care. Each shaft had to spin freely without wobbling. The slightest misalignment would cause the mechanism to jam or skip, producing errors that defeated the entire purpose. These were not mass-produced objects, but individual creations, assembled by hand, adjusted and readjusted until they operated smoothly. Owning one marked you as someone who dealt in quantities important enough to justify such expense. But even the finest mechanical calculator faced inherent limitations. Gears have mass, and mass has inertia. Trying to perform calculations quickly meant fighting against the physical resistance of metal against metal, springs compressed and released, momentum that had to be overcome with each new operation. The machines clicked and whirred as they worked, sound announcing effort, friction converting input into heat that served no computational purpose. Speed was bound by the rate at which physical components could move and settle. Accuracy depended on maintenance. Metal wears. Gears develop play in their fittings. Springs lose tension. A machine that calculated perfectly when new might introduce errors after years of use, its parts no longer meshing with the precision required for reliable carrying between positions. The devices needed periodic recalibration, comparison against known correct results, to verify they hadn't drifted into inaccuracy. Trust in mechanical calculation required trust in the physical integrity of many small parts working in concert. Despite these constraints, the machines proved their worth. Accounting offices adopted them. Engineering firms relied on them. Wherever numbers needed to be added, subtracted, or multiplied in volume, the mechanical calculator offered advantages over mental arithmetic alone. They were slow by standards we would later establish, but fast compared to human computers working with paper and pencil. They were expensive, but cheaper than the salaries of additional staff hired to perform the same work. They were imperfect, but their imperfections were at least consistent, predictable, correctable. The philosophical implication crept in slowly. A machine could perform reasoning, at least of a certain limited kind. It could follow rules. It could produce answers. True, it needed human guidance at every step, but the actual calculation, the transformation of input into output according to mathematical law, happened within the mechanism itself. We had created something that thought in a narrow sense, even if that thought was entirely determined by the arrangement of gears and the turn of a handle. The sand hadn't entered the picture yet, but we had begun to understand that thinking might be reproducible in systems that weren't alive. The notion that calculation could be reduced to pure logic, independent of any physical implementation, emerged from minds working with nothing but paper and abstract reasoning. If mathematical operations could be expressed as sequences of simple steps, and if those steps could be formalized as rules that never varied, then perhaps the process could be specified completely without reference to human insight or intuition. This was thinking about thinking, an attempt to describe the essence of computation separate from whoever or whatever performed it. The theoretical machines existed only as descriptions, logical architectures drawn out in notation that specified states and transitions and rules for moving between them. Imagine a ribbon of paper divided into squares, each square either marked or blank. Imagine a reader that examines one square at a time, that can mark or erase based on simple rules, that can shift left or right along the ribbon. These imaginary devices could, in principle, perform any calculation that could be specified through logical steps. They were universal, not because they were powerful, but because they were simple enough to be completely understood. What made these theoretical constructs significant was their demonstration that complexity could emerge from simplicity. A system with just a handful of basic operations, repeated and combined according to rules, could produce behaviors of arbitrary sophistication. You didn't need special mechanisms for different types of problems. You needed only the ability to follow instructions, to maintain state, to proceed step by step through a sequence that might be millions of operations long. The intelligence wasn't in any single step, but in the pattern of steps, the program that orchestrated simple actions into meaningful outcomes. This realization shifted how people thought about machines. Previous devices were built for specific purposes. A loom wove cloth, a printing press made copies of pages, a mechanical calculator added numbers. But a universal machine, even a purely theoretical one, could be configured to perform different tasks without rebuilding it. The same substrate could run different programs. The hardware remained constant, while the behavior changed, determined not by gears and levers, but by the sequence of instructions fed into it. Function became separable from form. The challenge was implementation. Theoretical universality meant nothing without physical realization, and every physical realization brought limitations. Early attempts used electromagnetic relays, switches that clicked open and closed as current flowed through coils. These were faster than gears, operating on the timescale of milliseconds rather than seconds. But they still involved physical movement. Contacts had to separate and connect. Armatures had to swing through space. Each operation produced sound, a clatter of metal on metal that filled rooms with industrial noise. Speed was still bound by the inertia of moving parts. Relays wore out. The contacts that made and broke circuits degraded with use, developing pits and burns from the tiny sparks that jumped when connections opened under load. A machine using thousands of relays needed constant maintenance, replacement of failed components, cleaning of contacts that had oxidized or accumulated debris. Reliability became a statistical problem. Each individual switch might fail rarely, but a system using tens of thousands of them would experience failures frequently. Error rates weren't measured per operation, but per hour of operation, with the expectation that something, somewhere in the vast clicking assemblage, would malfunction during any extended calculation. The physical size of relay-based machines became absurd. A computation that required thousands of simultaneous logical operations meant thousands of physical relays, each one the size of a human thumb. each one needing space for the coil, the armature, the contacts, the mounting hardware. The machines filled entire rooms, consuming power measured in kilowatts, generating heat that required ventilation systems just to prevent the components from cooking themselves into failure. The gap between theoretical elegance and practical engineering had never been wider. Yet even these clattering giants represented progress. They could be programmed, at least in a primitive sense. They could execute sequences of operations without human intervention beyond the initial setup. They could make decisions based on intermediate results, branching to different sequences of operations depending on whether a value was positive or negative, zero or non-zero. They could loop, repeating the same series of steps until a condition was met. These were the fundamental structures of computation, present in embryonic form, waiting for a substrate that could execute them without the overhead of mass and motion. The seed of the idea was planted. Thinking could be a process divorced from biology, implemented in any system capable of maintaining and manipulating symbolic states according to rules. The brain thought using neurons. Machines could think using relays, or perhaps someday using something else, something faster, something smaller, something that didn't require moving parts at all. The question wasn't whether such a substrate could exist. The question was whether we were clever enough to find it. The path to silicon began with glass, which is itself mostly silicon, though in a form that does nothing interesting electrically. Glass bulbs could be evacuated of air, creating vessels where electrons could move without colliding with gas molecules. Inside these vacuum tubes, a heated filament would emit electrons that could be steered, controlled, made to flow or stop flowing based on the voltage applied to intermediate grids. These were valves for electricity, switches with no moving parts in the mechanical sense, though the electrons themselves were always in motion, streaming from cathode to anode when the conditions permitted. Vacuum tubes operated on principles that seemed almost magical compared to relays. There was no physical contact to make or break, no spring to fatigue, no metal to pit from sparking. The switching happened in the behavior of electron clouds, particles too small to see responding to electrical fields. A small voltage on the control grid could govern a much larger current flowing through the tube, providing amplification as well as switching. This was faster than relays by orders of magnitude, operations completing in microseconds rather than milliseconds. Speed limited only by how quickly electrons could accelerate across the vacuum gap. But vacuum tubes brought their own catalogue of problems. They were fragile glass envelopes that could crack from thermal stress or mechanical shock. They consumed substantial power, the filaments needing to be heated to temperatures high enough to emit electrons freely, glowing orange in darkened rooms like tiny furnaces. This heat was wasted energy, shed into the surrounding air, requiring cooling systems to prevent the tubes from destroying themselves. A machine using thousands of vacuum tubes became a significant source of warmth, enough to heat the building that housed it during winter months. Reliability remained frustratingly probabilistic. Each tube had a finite lifespan, typically measured in thousands of hours. The filaments would gradually evaporate, thinning until they broke. The vacuum seal might leak, admitting air molecules that would scatter the electron stream and poison the carefully tuned electrical characteristics. The getter material inside the tube, there to absorb any stray gas molecules, would eventually become saturated and ineffective. A large computational machine might have tubes failing every few hours, requiring technicians to patrol the rows of equipment with testing devices, pulling suspect tubes and replacing them with fresh ones from stock. The physical form factor of vacuum tubes imposed constraints on how densely computation could be packed. Each tube needed space for the glass envelope, the base with its array of pins, the socket that held it in place. Heat dissipation required air circulation, spacing between components to prevent hotspots where tubes might cook themselves or their neighbors. The machines sprawled across rooms, racks of tubes arranged in rows, cables running overhead and beneath raised floors, power supplies humming as they converted alternating current into the various voltages needed to operate the tube heaters and plate circuits. Costs scaled with tube count. Each vacuum tube represented a manufactured component requiring precision glass blowing, careful evacuation, quality testing. The more complex the computation, the more tubes needed, and the budget climbed linearly with capability. Simple machines might use hundreds of tubes. More ambitious projects required thousands, then tens of thousands. The economics placed hard limits on what could practically be built. Some computations were theoretically possible, but financially absurd. Yet, for a period measured in decades, vacuum tubes represented the state of the art in electronic switching. They enabled calculations that would have been impossible with relays, problems in ballistics, cryptography, numerical weather prediction, aerodynamics. The machines were temperamental, expensive, and hungry for power, but they worked. They proved that electronic computation was viable, that problems could be solved faster than humans could solve them, that the theoretical architectures developed on paper could be implemented in hardware that, despite its flaws, could be made reliable enough to trust with important work. The limitations of vacuum tubes created the space for alternatives. Researchers understood what they needed: something that could switch quickly, that consumed less power, that didn't require heating, that could be manufactured smaller and cheaper, that didn't burn out after a few thousand hours. The wish list was clear. What wasn't clear was whether physics would permit such a device to exist, whether there was any phenomenon in nature that could be harnessed to switch electricity without the overhead of vacuum and heated filaments. The answer was buried in the strange behavior of certain materials, substances that conducted electricity, but not quite as well as metals, materials that occupied the ambiguous territory between conductors and insulators. The materials that would eventually replace vacuum tubes had been laboratory curiosities for decades before anyone understood their practical potential. Certain crystals exhibited electrical properties that varied depending on temperature, light exposure, or the presence of impurities. They weren't good conductors like copper, but they weren't insulators like glass either. They occupied a middle ground, their behavior complex and temperature dependent, difficult to predict or control with the precision that useful devices would require. The critical insight came from understanding these materials at the atomic level. In a pure crystal of silicon or germanium, atoms are arranged in a rigid lattice, each atom bonded to its neighbors in a repeating three-dimensional pattern. The electrons are mostly locked into these bonds, not free to wander through the material the way they do in metals. But at room temperature, thermal energy is enough to occasionally shake an electron loose, creating a mobile negative charge and leaving behind a positively charged hole where the electron used to be. Both the electron and the hole can move through the crystal, contributing to electrical conduction, though far less efficiently than in true metals. The transformation from curiosity to useful device required controlled contamination. By introducing tiny amounts of certain impurity atoms into the crystal lattice, the electrical properties could be deliberately altered. An atom with one extra electron compared to silicon would donate that electron to the crystal, creating an excess of negative charge carriers. An atom with one fewer electron would create holes, excess positive carriers. These doped regions could be precisely located within the crystal, creating junctions where regions of different character met. The junction itself became the active device, where a region rich in electrons met a region rich in holes. Something remarkable happened. Electrons from one side would diffuse across the boundary and fill holes on the other side, creating a thin zone depleted of mobile carriers. This depletion region acted as a barrier, resisting the flow of current in one direction while permitting it in the other. A small voltage applied across the junction could control a larger current flowing through it, providing the switching and amplification behavior needed for computation. But without vacuum, without heated filaments, without glass envelopes that could shatter. These solid-state devices were tiny compared to vacuum tubes. A transistor could be smaller than a match head, a speck of material with 3 wire leads attached. No moving parts, no vacuum to maintain, no filament to heat. The power consumption was measured in milliwatts instead of watts. The heat generated was minimal. The lifespan, as far as anyone could determine through testing, seemed to be effectively unlimited, barring physical damage. The contrast with vacuum tubes was so stark that early demonstrations seemed almost too good to be true. But manufacturing these devices reliably proved extraordinarily difficult. The crystal had to be extremely pure before doping, with impurity levels measured in parts per billion. Then the doping had to be controlled precisely, introducing exactly the right amount of the right elements in exactly the right locations. The processes involved growing crystals from molten material, slicing them into thin wafers, diffusing impurities through the surface at high temperatures, etching away unwanted regions, depositing metal contacts. Each step was sensitive to contamination, temperature variations, timing errors. Early transistors were produced individually, each one a custom creation that might behave slightly differently from its siblings, even when manufactured using identical processes. This variability made circuit design challenging. Engineers couldn't assume exact specifications, but had to design circuits that would function across a range of transistor characteristics. Testing and sorting became necessary, grouping devices by their measured parameters, setting aside the outliers that fell too far from the acceptable range. Manufacturing yields were low, costs high, though still cheaper than vacuum tubes when the total system cost was considered. The solid-state devices offered another advantage that wasn't immediately obvious. They could potentially be made smaller, much smaller. Vacuum tubes had a minimum practical size determined by the need to contain a useful vacuum volume and dissipate heat from the filament. Transistors had no such fundamental limit. The junction itself could be microscopic. The only constraint was how precisely you could control the manufacturing process, how accurately you could define regions of doped material separated by distances measured in microns rather than millimeters. If those manufacturing techniques could be refined, if the processes could be made reliable at smaller scales, then transistors could shrink far beyond what vacuum tubes ever could. This possibility hung in the air like a promise that seemed half fantasy. Imagine computation packed densely enough that thousands of transistors could fit in the space previously occupied by a single vacuum tube. Imagine the speed gains from shorter connection paths, the power savings from reduced scale, the reliability from eliminating thousands of potential failure points. The path forward was technically daunting, but at least it was a path. The materials existed. The physics was understood. What remained was engineering, the patient work of turning understanding into reproducible manufacturing, of making the difficult routine and the routine cheap. The individual transistor was an achievement, but computation requires thousands of components working in concert, connected in specific patterns that implement logical operations. Early circuits were assembled by hand, transistors soldered onto boards alongside resistors and capacitors, wires running between connection points like the rigging on a ship. This worked, but it was slow, error-prone, and fundamentally limited in scale. Each solder joint was a potential failure point. Each wire could be connected incorrectly. The density was constrained by how closely human fingers could place components and how precisely soldering irons could make connections without bridging adjacent points. The insight that changed everything was simple in concept, but brutal in execution. If you could build one transistor on a piece of silicon, perhaps you could build all the transistors for an entire circuit on the same piece. Instead of creating individual devices and wiring them together afterward, you could create the devices and the connections simultaneously using the same manufacturing steps. The substrate itself would contain everything: the active devices, the resistors, the capacitors, the wiring, all formed from layers of different materials deposited, patterned, and etched on the surface of a single crystal slice. This required rethinking manufacturing entirely. The processes used to make individual transistors had to be adapted to create multiple devices at once, each one precisely positioned relative to the others. The first step was growing a large crystal of silicon, a cylinder pulled slowly from molten material, atoms arranging themselves into perfect lattice order as they solidified. This crystal would be sliced into thin wafers, circular discs polished to near-perfect flatness. Each wafer would become the foundation for potentially hundreds of identical circuits, all manufactured in parallel. The patterns were created using photographic techniques adapted from the printing industry. A mask containing the desired pattern would be placed over the wafer surface, which had been coated with a light-sensitive material. Ultraviolet light shining through the mask would expose certain regions while leaving others protected. Chemical development would remove the exposed photoresist, revealing the silicon underneath in a precise pattern. This pattern could then guide etching processes that removed material, or doping processes that introduced impurities, or deposition processes that added new layers. Each circuit layer required its own mask, its own exposure, its own processing steps. The first layer might define where transistors would be located. The next might create the connections between them. Another might add a layer of insulation, then more connections on top of that insulation, creating multiple levels of wiring stacked vertically. Each layer had to align precisely with the layers below it, registration accurate to within fractions of a micron. Misalignment would cause connections to miss their targets, rendering the circuit non-functional. The chemical processes happened in rooms cleaner than hospital operating theaters. A single dust particle landing on a wafer during processing could create a defect that would ruin whatever circuit it touched. The air was filtered continuously, cycling through high-efficiency filters that removed particles down to microscopic sizes. Workers wore full body suits, gloves, masks, hairnets, booties, creating barriers between their contaminating human biology and the pristine silicon environment. Every surface was smooth, sealed, cleanable. Every chemical was purified to extreme levels. Every tool was designed to minimize particle generation. The wafers moved through the manufacturing process in carriers, batches being processed together through sequences of steps that could take weeks to complete, into furnaces for thermal oxidation, growing thin layers of silicon dioxide on the surface, into diffusion chambers where doping gases would penetrate into the crystal at high temperatures, into deposition chambers where metal would be sputtered onto the surface, atom by atom, into etching baths where precisely mixed acids would dissolve unwanted material. Each step was controlled to tight tolerances of temperature, time, pressure, chemical concentration. Defects were inevitable despite all precautions. A crystal imperfection in the starting material, a dust particle that evaded the air filters, a slight temperature variation during processing, an etching chemical that was mixed slightly wrong. Each defect would kill at least one circuit on the wafer, sometimes several if the flaw was large enough or occurred in a critical layer. The goal was to minimize defects, but perfection was impossible. Manufacturing yield became a critical metric. What percentage of circuits on a wafer actually worked when testing was complete? Testing happened after all processing was finished, after the wafer had been diced into individual chips. Tiny probes would touch down on each chip's connection points, running electrical tests to verify functionality. Working chips would be marked with a small dot of ink. Failed chips would be left unmarked. The yield might be 50% for a new design, improving to 80 or 90% as the manufacturing process matured and defect sources were identified and eliminated. The economics of integrated circuits depended heavily on yield. Low yields meant most of your expensive manufacturing effort was producing garbage. The working chips had to be removed from the wafer, a process that involved scribing lines between the circuits and breaking the silicon along those lines. The material was brittle, fracturing cleanly when stressed correctly, separating into individual rectangular dies. Each die was smaller than a fingernail, but contained thousands of transistors, interconnected in patterns that implemented the logic of computation. Handling these tiny fragments required precision tools, vacuum pickups that could grasp the chips without crushing them, placement systems that could position them accurately into packages. The packages were necessary because the silicon itself was too fragile and its connection points too small for practical use. Each chip would be mounted into a ceramic or plastic housing, bonded to a metal platform that would conduct heat away. Then the delicate work of wire bonding would begin, using equipment that could weld microscopically thin gold or aluminum wires between connection pads on the chip and pins on the package. These wires, finer than human hair, carried all signals between the silicon and the outside world. A typical chip might require dozens of these connections, each one made individually, each one critical to functionality. After wire bonding, a lid would seal the package, protecting the chip and its wire connections from moisture, dust, and physical damage. Some packages used ceramic lids brazed in place in a high-temperature furnace. Others used metal lids welded on in an inert atmosphere. The cheapest packages simply molded plastic around the entire assembly, encapsulating everything in a protective cocoon of epoxy resin. The package choice affected cost, reliability, and how much heat the chip could dissipate during operation. High-performance parts needed expensive packages with good thermal characteristics. Simple parts could survive in cheap plastic. The manufacturing complexity meant that months could pass between starting a wafer and delivering finished packaged parts ready for use. The pipeline was long, containing wafers at various stages of processing. A contamination event that ruined wafers might not be discovered until weeks later when those wafers reached testing. By then, many more wafers following the same process might already be contaminated, their fate sealed, even though they were still moving through the manufacturing sequence. Managing this pipeline required careful tracking, documentation of every process step, statistical analysis to detect problems before they consumed too much production capacity. Scale became essential to economic viability. The masks used to pattern wafers were expensive, created using precision optical or electron beam equipment. A complete mask set for a complex chip might cost hundreds of thousands, later millions. These costs could only be amortized across large production volumes. Making a few hundred chips was economically absurd. Making millions made sense. This drove consolidation in the industry, favoring companies that could build large factories and keep them running at high capacity, spreading fixed costs across maximum output. The factories themselves represented staggering capital investments. The clean rooms with their air filtration systems, the process equipment, each machine costing more than a house, the quality control labs, the utilities, infrastructure to supply ultra-pure water, specialty gases, electrical power at stable voltages. A fabrication facility could cost billions, and its equipment would begin to obsolete the moment it was installed, as newer processes enabled smaller features and higher performance. The economic pressure to keep equipment productive was intense. Miniaturization proceeded according to a pattern that would become predictable. Each generation of manufacturing technology could create features smaller than the previous generation. Smaller features meant transistors could be packed more densely. More transistors in the same area meant more computational capability per chip. More capability meant faster processors, larger memories, more complex functions integrated onto single pieces of silicon. The improvement wasn't steady, but arrived in steps. Each new process technology representing years of development work to shrink dimensions while maintaining or improving yield. The limit seemed always to be approaching, but never quite arriving. Engineers would declare that the current generation was nearing the edge of what physics allowed, that you couldn't make features much smaller without encountering fundamental barriers. Then someone would discover a new trick, a new material, a new process that pushed the boundary further out. Lithography wavelengths got shorter, moving from visible light to ultraviolet to deep ultraviolet to extreme ultraviolet. Each transition requiring completely new equipment and optical systems. Feature sizes that seemed impossibly small became routine, then obsolete, then quaint. The silicon wafers themselves grew larger over time, driven by economics. A larger wafer could hold more chips, spreading the per-wafer processing cost across more units. The industry moved from wafers barely larger than a cookie to dinner plate-sized discs to sizes that required both hands to hold safely. Each increase in wafer size required upgrading every piece of process equipment, every handling system, every cassette and carrier. The transitions were expensive, but paid for themselves through improved manufacturing efficiency, more chips per unit of factory capacity, better economics that enabled lower prices and higher volumes. The early integrated circuits were custom creations, each one designed for a specific purpose, manufactured in small volumes for particular applications. A chip designed for a calculator couldn't be used in a radio. A circuit optimized for signal processing had no role in a digital clock. This specialization made sense for the first few generations, when design tools were primitive and manufacturing capacity was limited, but it created inefficiency. Every new product required new silicon, new masks, new manufacturing qualification, new testing procedures. The alternative was to build general-purpose circuits, chips that could be configured to perform different tasks depending on how they were used. The logic elements would be standardized, identical blocks repeated across the silicon surface, connected through a flexible architecture that could be programmed rather than hardwired. This required a conceptual shift from thinking of circuits as fixed structures to thinking of them as platforms that could execute different sequences of operations. The hardware would be universal. The specificity would come from software, from the patterns of instructions fed into the chip during operation. The memory circuits came first in this direction. A memory chip didn't need to know what data it was storing. It simply needed to accept addresses and read or write values at those locations. Whether the data represented numbers, text, images, or instructions was irrelevant to the silicon. The same memory architecture could serve countless different applications. Manufacturing memory chips in large volumes became economically viable because one design could address many markets. Scale drove costs down, making memory cheap enough to use generously rather than parsimoniously. The processors followed a similar logic, but with greater complexity. A processor needed to fetch instructions, decode what those instructions meant, execute the specified operations, and store the results. The instruction set, the vocabulary of operations the processor could perform, had to be defined carefully, comprehensive enough to be useful, but simple enough to implement efficiently in silicon. Early instruction sets were minimalist, offering only basic operations: add, subtract, move data, compare values, jump to different locations in the program based on conditions. These instruction sets became specifications that software could target. If you wrote a program using only the defined instructions, it would run on any processor that implemented that instruction set, regardless of which company manufactured the chip or what generation of manufacturing technology it used. This compatibility created leverage. Software written once could run on many machines. Applications could be developed independently of hardware, sold to users who owned compatible processors. The division between hardware and software became cleaner, each layer able to evolve somewhat independently of the other. Standardization extended beyond individual chips to the systems built from them. The physical packaging needed standards so that chips from different manufacturers could plug into the same sockets. The electrical signaling needed standards so that components could communicate reliably, regardless of who made them. The timing needed standards so that faster chips could work with slower memories without constant synchronization failures. These standards emerged through a combination of industry cooperation and market dominance, with successful approaches becoming de facto requirements through widespread adoption. The bus architectures that connected components together became another focus of standardization. A bus was simply a shared set of electrical connections that multiple components could use to exchange data, but the details mattered enormously. How many parallel wires carried data? How was addressing handled? How did components signal that they wanted to use the bus? How were conflicts resolved when multiple components tried to communicate simultaneously? Each of these questions needed answers that balanced performance, cost, and complexity. Standards, documents proliferated, thick specifications that defined every detail of how components should behave. The electrical characteristics, voltage levels, current drive capability, input impedance, capacitive loading limits, the timing requirements, setup times, hold times, maximum propagation delays. The protocol details, sequence of signals for read operations, for write operations, for special cases and error conditions. Implementing a standard correctly required careful attention to these specifications, testing to verify compliance, often certification processes to confirm compatibility. The benefits of standardization weren't purely technical. They enabled a supplier ecosystem where multiple companies could manufacture compatible components, creating competition that drove prices down and innovation up. A customer wasn't locked into a single vendor, but could choose between alternatives that offered different balances of performance, power consumption, cost, and features. This competitive dynamic accelerated improvement as manufacturers raced to offer better specifications while maintaining compatibility with the established standards. But standardization also created inertia. Once a standard became widely adopted, changing it became difficult. Existing software depended on the defined instruction set. Existing hardware assumed particular electrical characteristics. Existing systems were built around specific bus architectures. Improvements that would break compatibility with the installed base faced resistance, even when they offered significant advantages. The standards tended to accumulate features over time. New capabilities added in ways that maintained backward compatibility, creating architectures that grew increasingly complex as they evolved. The tension between optimization and compatibility shaped how silicon evolved. Engineers could see ways to design faster processors, more efficient instruction sets, better bus architectures, but implementing these improvements often meant breaking with existing standards. The cost of incompatibility was real. Software that would need rewriting, peripheral devices that would become obsolete, customer resistance to changes that invalidated their existing investments. The temptation was strong to maintain continuity, even when it meant carrying forward suboptimal design choices. Some standardization happened at the level of manufacturing processes themselves. The tolerances for silicon purity, the specifications for photoresist materials, the chemical compositions of etching solutions. These became shared knowledge across the industry, refined through collective experience and documented in process handbooks that grew thicker with each generation. Suppliers of manufacturing equipment built their tools to support these standard processes, creating an infrastructure that worked for the industry as a whole rather than being optimized for individual companies. The standardization of testing methodologies ensured that chips from different manufacturers could be compared meaningfully. What did it mean for a processor to run at a particular clock speed? How was power consumption measured? What temperature range constituted acceptable operating conditions? These questions needed consistent answers so that specifications meant the same thing regardless of who published them. Industry organizations developed test procedures, benchmark programs, measurement techniques that provided common baselines for evaluation. Quality standards addressed the statistical nature of semiconductor manufacturing. No process was perfect. Some percentage of manufactured parts would fail, but how failure was defined and measured needed standardization. The industry settled on metrics like defects per million, measured under specific conditions over specific time periods. A chip might be rated for a certain mean time between failures, a statistical prediction of reliability based on accelerated lifetime testing, where parts were stressed at elevated temperatures and voltages to induce failures faster than they would occur under normal use. The environmental standards emerged more slowly, addressing what happened to silicon after its useful life ended. The materials used in manufacturing included toxic chemicals, heavy metals, substances that couldn't simply be dumped into landfills without environmental consequences. Standards for handling electronic waste, for recycling materials, for reducing hazardous substances in manufacturing processes came under regulatory pressure and industry self-regulation. The externalities of silicon fabrication couldn't be ignored indefinitely. Documentation standards determined how chip designs were communicated between teams, between companies, across generations of engineers. Schematic symbols for transistors, logic gates, memory blocks, file formats for mask data, for test vectors, for timing specifications, design languages that could describe circuits at various levels of abstraction, from the behavior you wanted to the exact transistor-level implementation. These standards enabled collaboration at scale, allowing large designs to be partitioned across many engineers working in parallel. The standardization of power delivery might seem mundane, but proved critical to practical deployment. Chips needed stable voltage supplies, free from noise and fluctuation. The standards specified acceptable voltage ranges, maximum ripple tolerances, transient response requirements. They defined how power should be distributed across the chip, how decoupling capacitors should be placed, how ground connections should be arranged to minimize electrical noise. Poor power delivery could cause erratic behavior, timing failures, or outright damage to the silicon. Clock distribution standards address the challenge of keeping billions of transistors synchronized. Every flip-flop in a digital circuit needed to sample its input at precisely the right moment. determined by the clock signal. But clock signals had to propagate across the entire chip, and electrical signals travel at finite speed. Standards evolved for how clock networks should be designed, how buffers should be placed to restore signal quality, how much variation in clock arrival time, skew, was acceptable. Managing these timing constraints became one of the most challenging aspects of chip design. Interface standards multiplied as chips needed to communicate with an expanding variety of peripherals and other chips. Standards for connecting to memory, to storage devices, to displays, to network interfaces, to sensors, to user input devices. Each interface had its own consortium or standards body, its own set of specifications, its own compliance testing regime. A modern processor might need to implement dozens of different interface standards to be compatible with the ecosystem of components it might need to work with. The proliferation of standards created its own problems. Compliance was expensive, requiring careful design work and extensive testing. Small companies struggled to implement the full range of standards, creating barriers to entry that favored large, established manufacturers. The standards themselves sometimes conflicted, requiring awkward compromises or choosing to support some standards while ignoring others. The ideal of universal compatibility remained elusive, replaced by the reality of partial compatibility across overlapping ecosystems of semi-compatible components. The shift from silicon as a laboratory material to silicon as the foundation of everyday objects happened without announcement, without ceremony, without most people noticing it was occurring. The chips appeared first in places where their presence was invisible, inside telephone switching equipment, buried in industrial control systems, embedded in military hardware. These were not consumer goods. They were infrastructure components, boxes in climate-controlled rooms, systems maintained by specialists who understood their function but might never see the silicon inside. The calculator was perhaps the first object that brought integrated circuits into direct human contact at scale. Early models were desk-sized machines that could perform basic arithmetic, their capability modest, but their price point accessible to businesses that needed to process numbers regularly. As manufacturing improved and costs declined, the calculators shrank. Within a few years, a device that could add, subtract, multiply, and divide fit in a briefcase, then in a pocket, then on a wristwatch. The silicon inside became cheaper than the plastic case that held it. What made this transition remarkable was its ordinariness. People didn't marvel at the integrated circuits inside their calculators any more than they marveled at the metallurgy in their spoons. The technology became infrastructure, assumed and unremarked upon. You pressed buttons. Numbers appeared on a display. The mechanism that made this happen was irrelevant to the user experience. The silicon had achieved the ultimate success of any technology. It disappeared into the background, becoming invisible precisely because it worked reliably enough to be taken for granted. Watches followed a similar trajectory. Mechanical movements, intricate assemblages of gears and springs that required skilled craftsmanship to manufacture and adjust, were replaced by quartz crystals and simple integrated circuits. A watch with no moving parts except the battery-powered hands could keep time more accurately than expensive mechanical chronometers. The craftsmanship moved from the visible mechanics to the invisible electronics, from adjusting hairsprings to designing oscillator circuits. The change was cultural as much as technical, a shift in what qualities were valued. The digital watch, with its numeric display and button-activated functions, made the presence of computation explicit. Pressing a button to see the date or activate a stopwatch was interacting with a processor, even if a simple one. The watch could store multiple time zones, count down from a set interval, beep at programmed times. These were computational tasks, executed by silicon small enough to fit behind a watch face, consuming so little power that a coin cell battery could run it for years. The threshold of what qualified as a computer blurred and then dissolved. Home appliances began incorporating silicon controls, replacing electromechanical timers and thermostats with programmable alternatives. A washing machine could remember cycle preferences, adjusting water temperature and spin speed based on the selected program. A microwave oven could coordinate power levels and timing, switching between heating and resting periods to defrost food more evenly than a simple timer allowed. These were not marketed as computers, but as appliances with convenient features. The silicon inside merely an implementation detail. The automotive industry embraced integrated circuits for functions where reliability was critical, and mechanical solutions were becoming unworkable. Engine control units monitored sensors measuring airflow, oxygen levels, engine temperature, throttle position, using this information to adjust fuel injection timing and quantity thousands of times per second. The calculations were simple, but they had to be fast and they had to be correct. An error could damage the engine or create dangerous operating conditions. Silicon proved more reliable than the mechanical systems it replaced, less prone to drift and wear. Anti-lock braking systems demonstrated silicon managing real-time control of physical processes at speeds beyond human reaction time. Sensors at each wheel monitored rotation, detecting when a wheel was beginning to lock during braking. The control unit would pulse the brake pressure at that wheel, maintaining it at the edge of traction, optimizing stopping distance while preserving steering control. This happened dozens of times per second, faster than any mechanical system could respond. Certainly, faster than a human driver could pump the brakes manually. The silicon was preventing accidents, saving lives, doing so invisibly from its housing under the hood. Entertainment systems brought silicon into leisure activities. Video game consoles contain processors powerful enough to generate animated graphics, respond to controller inputs with minimal latency, produce synchronized sound effects and music. The experience was interactive in ways that passive media like television couldn't match. Children who grew up with these devices developed intuitions about computational systems, about inputs and outputs, about the relationship between actions and results mediated through silicon processors. They were learning to think computationally without formal instruction, through play. The personal computer represented silicon's arrival as a general-purpose tool accessible to individuals rather than institutions. Early models were kits requiring assembly, sold to hobbyists who understood electronics and could solder components onto circuit boards. These were not mass-market devices, but experiments, platforms for exploration by people curious about what could be done with a processor under direct user control. The software was often written by the users themselves, programs tailored to specific needs or interests. As manufacturing costs continued falling, computers transitioned from kits to assembled units, from hobby projects to commercial products. The form factor standardized around a keyboard for input, a display for output, some form of storage for programs and data. The capabilities remained modest by later standards. Memories measured in kilobytes, processors running at speeds measured in megahertz, storage on magnetic media that held less than a modern photograph file. But the trajectory was clear. Each generation offered more capability at lower cost. The software ecosystem that developed around personal computers created value beyond the hardware itself. Programs for word processing eliminated typewriters and correction fluid, making text editing a process of moving blocks of information rather than retyping entire pages. Spreadsheet programs enabled financial modeling, calculation tables where changing one value would automatically update all dependent calculations. These applications demonstrated computational leverage, where silicon amplified human capability in specific domains, automating tedious work and enabling analysis that would be impractical manually. The communications capabilities arrived gradually, first through modems that converted digital data into audio tones that could travel over telephone lines designed for voice. The speeds were glacial by later standards, but the ability to exchange information between computers opened new possibilities. Bulletin board systems allowed users to post messages, share files, communicate asynchronously with others who had similar interests. These were proto-networks, precursors to what would become ubiquitous global connectivity. Silicon found its way into communication infrastructure itself, not just in the devices at the endpoints, but in the switching systems, the routing equipment, the base stations for mobile phones. The telephone network transitioned from analog circuits and mechanical switches to digital systems where conversations were sampled, converted to numbers, transmitted as data packets, and reconstructed at the destination. The voice quality improved while the infrastructure became more flexible, capable of carrying data alongside voice, eventually rendering the distinction between voice and data communication obsolete. Mobile phones represented silicon's penetration into constant personal accompaniment. Early models were portable in the sense that a briefcase is portable, heavy, bulky, with battery life measured in minutes of talk time. But the miniaturization continued relentlessly, driven by advances in silicon integration and battery technology. Phones shrank to pocket size, then became lighter than a deck of cards, then gained features beyond voice communication. Text messaging, basic web browsing, email access, calendar functions, games. The camera's transition to digital capture demonstrated silicon replacing not just mechanical systems, but chemical ones. Photographic film, with its light-sensitive silver compounds and elaborate development chemistry, gave way to silicon sensor arrays, where each pixel was a photodiode measuring light intensity. The image was captured as numbers, stored in memory, could be viewed immediately rather than waiting for chemical processing. The feedback loop between capture and viewing shortened from hours to seconds, changing how people approached photography. Music players followed a similar path from mechanical to digital. Vinyl records played by needles tracing grooves gave way to optical discs read by lasers, which gave way to solid-state memory storing music as compressed data files. The entire music collection that once required shelves of physical media could fit on a chip the size of a fingernail. The distribution shifted from physical objects sold in stores to data files transmitted over networks. The tangible artifact of the album reduced to metadata and binary encodings of sound waves. Each of these transitions involved silicon becoming more capable, more integrated, more essential to the function of the device. The chips were growing more complex, even as they shrank physically, packing more transistors into less space, running faster, consuming less power. The improvement wasn't linear, but exponential, each generation roughly doubling the capability of the previous generation, a pattern that held for decades and trained an entire industry to expect continuous acceleration. The environmental footprint of this proliferation remained largely invisible during the expansion. The energy consumed by data centers, the resources required for manufacturing, the electronic waste accumulating as devices obsolesced. These costs were externalized, not reflected in purchase prices, easy to ignore when the benefits were immediate and the consequences diffuse. The true cost of teaching SAN to think extended far beyond the price of the chips themselves, into supply chains that spanned the globe and environmental impacts that would persist for generations. The individual chip, for all its complexity, cannot function in isolation. It requires power delivery systems that can supply stable current at precise voltages, varying from a few volts down to fractions of a volt as silicon scaled smaller. The power has to arrive without fluctuation, without noise, responding instantaneously to changes in demand as the processor switches between idle and active states. This required not just adequate supply, but sophisticated regulation. Circuits that monitored voltage levels thousands of times per second and adjusted current delivery to maintain stability. The circuit boards that hosted these chips became engineering challenges in their own right. A modern board might contain 10 or more layers of copper traces, sheets of conductive material separated by insulating substrate, connected through thousands of tiny drilled holes plated with metal. The traces had to be routed to avoid interference, to maintain controlled impedance for high-speed signals, to minimize the distance that critical signals traveled. The layout was planned by software that could manage the complexity of thousands of connections, optimizing for electrical performance, manufacturability, and thermal management simultaneously. Heat removal limited how much power could be concentrated in small spaces. A processor running at full capacity might dissipate 100 watts or more, power density approaching that of a stovetop burner, all concentrated in a chip the size of a postage stamp. Without cooling, the silicon would destroy itself in seconds, temperatures rising past the point where the semiconductor properties broke down and the physical structure began to degrade. Heat sinks, blocks of metal with fins to increase surface area, drew heat away from the chip and dispersed it into moving air. The cooling systems evolved from passive heat sinks to active solutions incorporating fans, then to more exotic approaches for high-performance applications. Heat pipes, sealed tubes containing fluid that evaporated at the hot end and condensed at the cool end, transported thermal energy more efficiently than solid metal. Liquid cooling systems pumped water or specialized coolants through channels in contact with the chip surface, carrying heat to remote radiators where it could be dissipated without the space constraints of air cooling. Data centers experimented with immersion cooling, submerging entire servers in non-conductive fluids. The power infrastructure extended beyond individual machines to the facilities that housed them. Data centers consumed electricity measured in megawatts, requiring substations, backup generators, uninterruptible power supplies that could bridge the gap during outages, battery banks that could support operations for minutes or hours until generators spun up to speed. The power had to be clean, free from surges and sags that could cause computational errors or damage equipment. Entire systems existed solely to condition and protect the electricity supply. Cooling at data center scale meant moving tremendous volumes of air or water. Fans pulled outside air through filters and across equipment racks. The warm exhaust vented back outside or through heat exchangers. In hot climates or during peak demand, mechanical cooling systems using compressors and refrigerants augmented or replaced air circulation. The energy consumed by cooling often rivaled the energy consumed by the computation itself, a hidden cost of silicon's power appetite. Efficiency improvements in cooling infrastructure translated directly to reduced operating costs. The network infrastructure connecting these computational resources formed a layered hierarchy of cables, switches, routers, and protocols. Within a building, copper cables or fiber optics linked machines together at speeds measured in gigabits per second. Between buildings, Between cities, fiber optic cables carried light pulses encoding data, thousands of simultaneous wavelengths multiplexed onto single fibers to maximize capacity. Undersea cables crossed oceans, physically connecting continents. The global network mapped onto actual physical infrastructure, vulnerable to ship anchors, earthquakes, and intentional sabotage. The switching equipment that routed data through this network contained its own silicon, specialized chips optimized for moving packets of information from input ports to output ports at line speed. These switches had to make routing decisions in nanoseconds, examining packet headers, consulting routing tables, forwarding data toward its destination, without introducing delays that would be noticeable to applications. A single large switch might contain dozens of specialized chips working in parallel, collectively handling traffic volumes that would saturate any individual processor. Storage infrastructure provided the persistence that computation required. Data had to survive power cycles, had to be accessible across timescales from milliseconds to decades. Solid-state drives using flash memory offered fast access, but wore out after limited write cycles. Magnetic hard drives stored more data per dollar, but required spinning platters and moving read heads, mechanical components that made them slower and less shock-resistant. Tape archives provided bulk storage for rarely accessed data. Sequential access traded for density and cost advantages. Each storage technology had its niche, its appropriate use cases. The backup and redundancy systems acknowledged that all hardware eventually fails. Data that mattered was stored in multiple locations, synchronized continuously so that the loss of any single storage device wouldn't result in data loss. RAID arrays striped data across multiple drives with parity information that could reconstruct lost data if a drive failed. Geographic distribution placed copies in different buildings, different cities, different regions, protecting against localized disasters. The cost of redundancy was justified by the value of the data being protected. The software infrastructure that managed physical resources operated in layers of abstraction, each level hiding complexity from the level above. At the lowest level, firmware embedded in hardware devices knew how to initialize components, how to respond to basic commands, how to report status and errors. Above that, operating system kernels managed access to hardware resources, scheduling which programs could use the processor when, allocating memory, coordinating access to storage and network interfaces. Device drivers translated between the generic interfaces that operating systems provided and the specific requirements of individual hardware components. A network card from one manufacturer required different initialization sequences, different command protocols, different interrupt handling than a card from another manufacturer. But the operating system could treat them identically because the driver layer absorbed those differences. This allowed hardware to evolve independently of the software that used it, as long as drivers were updated to support new capabilities. File systems impose structure on the raw storage, organizing bytes into files and directories, maintaining metadata about creation times and access permissions and modification history. These systems had to balance performance against reliability, caching data in memory for speed, while ensuring that power loss wouldn't corrupt the stored information. Journaling systems logged intended changes before applying them, allowing recovery from interruptions. Copy-on-write systems never modified data in place, but always wrote new versions, making it impossible for partial writes to damage existing data. The network protocols that governed communication between machines operated through negotiated agreements about how to format data, how to handle errors, how to manage flow control when receivers couldn't keep up with senders. Each protocol layer added its own headers and trailers, wrapping the payload in increasingly detailed envelopes as it moved down the stack from application to physical transmission. At the destination, the reverse process unwrapped the layers, each one stripping off its own metadata and passing the remaining payload upward. Virtualization systems created the illusion of multiple independent machines running on single physical hardware. The physical processor's time was divided among virtual machines, each one given the impression it had exclusive access to hardware resources. Memory was partitioned, address spaces isolated so that one virtual machine couldn't interfere with another. Storage and network access were mediated through virtual interfaces that looked like dedicated hardware to each guest system. This enabled more efficient use of physical resources, consolidating workloads that didn't fully utilize individual machines. Container systems took virtualization further, sharing the operating system kernel across isolated application environments. Each container had its own file system view, its own network identity, its own process space, but used the shared kernel underneath. This reduced overhead compared to full virtualization, allowing higher density of isolated workloads on the same hardware. The containers could be started and stopped in seconds, moved between machines, scaled up and down dynamically in response to demand. The orchestration systems that managed fleets of containers automated deployment, scaling, and recovery. They monitored application health, restarting failed instances, redistributing load when capacity changed, upgrading software versions without downtime by gradually replacing old containers with new ones. These systems treated individual machines as fungible resources, pools of computation and memory to be allocated as needed, rather than carefully managed individual servers with known identities. The monitoring infrastructure tracked everything: CPU utilization, memory pressure, network bandwidth, storage latency, application error rates, user activity patterns. Metrics flowed into time series databases optimized for handling streams of numerical measurements, systems that could compress the data while preserving the ability to query it at various aggregation levels. Dashboards displayed current status. Alert systems notified operators when metrics exceeded thresholds, indicating problems. The continuous integration and deployment pipelines automated the process of turning source code into running applications. Code changes triggered automated builds, compiling source into executable form. Automated tests verified that the changes hadn't broken existing functionality. Successful builds were packaged into container images and deployed to staging environments for further testing. Passing all validation, the changes would be promoted to production, rolled out gradually, while monitoring confirmed the new version performed as expected. The infrastructure as code movement treated system configuration as source code, version controlled and tested like application code. The desired state of the infrastructure was declared in configuration files, and automation would reconcile the actual state with the desired state, creating resources that didn't exist, modifying resources that differed from specification, removing resources no longer needed. This made infrastructure reproducible, recoverable from disasters by reapplying the configuration rather than manually rebuilding systems. Security infrastructure protected against threats both external and internal. Firewalls filtered network traffic, blocking connections that didn't match allowed patterns. Intrusion detection systems analyzed traffic for signatures of known attacks or anomalous patterns suggesting new threats. Encryption protected data in transit and at rest, rendering it unreadable without the correct decryption keys. Authentication systems verified user identities. Authorization systems determined what verified users were permitted to access. Audit logs recorded activity for later review. Accountability enforced through comprehensive tracking. The network that connected computational resources across the planet emerged from modest beginnings. Research institutions sharing information across dedicated lines. Universities collaborating on projects that required exchanging data too large for postal delivery. The protocols were experimental, the topology simple, the traffic measured in kilobits per second when it flowed at all. The vision was grander than the implementation, imagining a future where information could move freely between machines, regardless of physical location. But the reality was limited by the available infrastructure. The transition to commercial viability happened gradually, driven by decreasing costs of network equipment and increasing value of connectivity. Businesses discovered that connecting their locations allowed centralized data processing, inventory management across distributed warehouses, communication between offices without long-distance telephone charges. The economic justification strengthened as the applications multiplied, each new use case making the network infrastructure more valuable, justifying further investment in capacity and reliability. The physical topology grew organically rather than according to central planning. Cables were run where demand justified the cost, creating uneven coverage that favored dense urban areas over rural regions. International connections followed existing infrastructure when possible. Telephone cables and satellite links repurposed to carry data traffic. New cables were laid along rail lines, buried alongside highways, strung from utility poles, following paths of least resistance through regulatory environments and physical geography. The backbone networks that carried bulk traffic between regions used fiber optic cables capable of transmitting data at speeds that would have seemed impossible just years earlier. Multiple fibers bundled together, each carrying dozens or hundreds of wavelengths of light simultaneously, each wavelength modulated to carry independent data streams. The capacity of a single cable could exceed the total global network capacity from previous decades, yet demand grew to fill the available bandwidth as applications adapted to treat network accessor as abundant rather than scarce. The routing infrastructure that directed traffic through this maze of connections operated through distributed decision-making. No central authority determined the path packets would take from source to destination. Instead, routers exchanged information about which networks they could reach, building tables that mapped destinations to next hop addresses. The routes adapted automatically to failures, traffic flowing around broken links or overloaded nodes, resilience emerging from the protocol design rather than requiring manual intervention. The addressing system that identified every connected device had to scale from thousands of connected machines to billions. The original addressing scheme proved inadequate as the network grew, its limited address space insufficient for the explosion of connected devices. The transition to a new addressing system with vastly more capacity happened slowly, requiring updates to network equipment, operating systems, applications, a gradual migration that took decades and remained incomplete long after the new system was technically available. The domain name system provided a layer of indirection between human-readable names and numerical network addresses. Rather than remembering strings of numbers, users could reference machines and services by names that carried meaning. The resolution from names to addresses happened through a distributed database, hierarchically organized, cached aggressively for performance. This system became critical infrastructure, a single point of conceptual failure, even though the implementation was distributed, because the entire network depended on accurate name resolution. The content delivery networks optimized for distributing popular data to users scattered globally. Rather than serving all requests from a single origin, content was replicated to edge servers located close to users, reducing latency and distributing load. These networks used sophisticated routing to direct users to the nearest available copy, adapting to traffic patterns and server availability. A single piece of content might be served from hundreds of different physical locations, the end user unaware that the data came from a nearby cache rather than the original source. The mobile networks that provided connectivity to portable devices added another layer of complexity. Devices moved between coverage areas, switching seamlessly between cell towers without dropping connections. The network tracked device locations, routing incoming traffic to the current serving tower, handling the protocol details required to maintain sessions across physical mobility. The radio spectrum was divided among carriers, allocated by regulatory authorities, making it a finite resource that had to be shared efficiently. The satellites that provided connectivity in regions without terrestrial infrastructure operated in various orbital configurations. Low Earth orbit satellites moved quickly across the sky, requiring frequent handoffs between satellites as each one passed out of view. Geostationary satellites remained fixed relative to ground positions, but introduced latency from the long round trip to orbital altitude and back. The trade-offs between coverage, capacity, latency, and cost shaped which approach made sense for different applications and regions. The protocols that governed communication across this heterogeneous network infrastructure had to accommodate vast differences in link speeds, latency, and reliability. A connection might traverse fiber optics running at gigabits per second, satellite links with hundreds of milliseconds of delay, congested wireless networks with high packet loss rates. The protocol stack absorbed these variations, adapting transmission rates to available capacity, retransmitting lost data, reordering packets that arrived out of sequence. The congestion control mechanisms prevented the network from collapsing under excessive load. When too much data tried to traverse a link, packets would be dropped, signaling to senders that they should reduce their transmission rate. This happened automatically, without central coordination, each sender reducing its rate when it detected packet loss, increasing gradually when packets flowed successfully. The equilibrium was dynamic, shifting as traffic patterns changed, as routes adapted to failures, as new flows started and existing flows completed. The encryption systems that protected data in transit evolved from optional security measures to mandatory components of network communication. The computational cost of encryption, once significant enough to discourage its use except for sensitive data, became negligible as processors grew faster and specialized cryptographic accelerators were integrated into network hardware. The default shifted from transmitting data in clear text to encrypting everything, eliminating entire classes of eavesdropping attacks by denying attackers access to unencrypted traffic. The certificate authorities that vouched for the identity of network services formed a trust hierarchy critical to secure communication. Browsers and operating systems shipped with root certificates for trusted authorities, which could sign certificates for specific services, creating chains of trust from globally recognized routes to individual websites. Compromising this system meant breaking the foundation of secure network communication, making the security of certificate authorities a matter of global importance. The content filters and firewalls that controlled what could traverse network boundaries reflected policy decisions as much as technical requirements. Some restrictions aimed at security, blocking known malicious traffic, or limiting exposure of internal systems to external access. Others enforced social or political preferences, blocking access to content deemed objectionable by governments or organizations. The technical mechanism was similar. The justification and consequences differed dramatically. The network addressed translation systems that allowed multiple devices to share single public addresses, enabled the continued growth of the network despite address space limitations. Internal networks use private address ranges, with translation devices mapping outbound connections to public addresses dynamically. This solved immediate scaling problems, but complicated protocols that embedded addresses in their payloads, breaking assumptions about end-to-end addressability that some applications depended on. The quality of service mechanisms that prioritized certain traffic types over others acknowledged that not all data had equal time sensitivity. Video conferencing required low latency, but could tolerate some packet loss. File transfers could accept variable latency, but needed reliable delivery. Interactive gaming demanded both low latency and reliable delivery. The network could be configured to recognize these different requirements, allocating bandwidth and queue priority accordingly, though actually implementing fair prioritization remained technically and politically contentious. The peer-to-peer networks that distributed load across participating nodes, rather than concentrating it in central servers, demonstrated alternative architectural approaches. Each participant contributed resources, storage, bandwidth, processing power to the collective system. Content was discovered through distributed search, retrieved from whichever peers happened to have it available. This scaled well for popular content, replicated across many peers, but struggled with rare content that few peers held. The overlay networks that created virtual topologies atop the physical network enabled new capabilities without requiring changes to underlying infrastructure. Virtual private networks encrypted traffic between endpoints, creating secure channels across untrusted networks. Content distribution overlays optimized routing for specific traffic patterns. Anonymity networks bounce traffic through multiple intermediaries to obscure the origin and destination of communications. Each overlay implemented its own routing, its own addressing, its own protocols, independent of the network layer below. The Internet of Things expanded the network to include devices that weren't computers in the traditional sense. Sensors reporting temperature or humidity or motion, actuators controlling physical systems, cameras capturing images, industrial equipment reporting status. These devices often had limited computational resources, minimal power budgets, intermittent connectivity. Protocols designed for powerful machines with reliable connections had to be adapted or replaced with lightweight alternatives suitable for constrained devices. The mesh networks that allowed devices to route traffic through each other extended connectivity into areas without fixed infrastructure. Each node could forward traffic for its neighbors, creating paths through multiple hops between endpoints. The topology adapted automatically as devices moved or failed, routes reforming around gaps in coverage. This resilience came at the cost of reduced capacity. Each hop consumed wireless bandwidth, but enabled connectivity where centralized infrastructure couldn't reach, or where infrastructure had failed. The satellite internet constellations being deployed promised global coverage at lower latency than traditional geostationary satellites, using large numbers of low Earth orbit satellites to create mesh networks in space. The technical challenges included coordinating thousands of satellites, managing handoffs as satellites moved across the sky, delivering ground station equipment to end users, avoiding orbital debris and collisions. The scale of deployment rivaled historical infrastructure projects, requiring sustained investment over years to reach operational capability. The question of whether silicon could truly think or merely simulate thinking through sufficiently complex arrangements of simple operations remained philosophically unresolved, even as the practical capabilities expanded. The transistors themselves knew nothing, understood nothing, experienced nothing. They switched between conducting and non-conducting states based purely on electrical conditions, electrons flowing or not flowing according to the laws of physics. No individual transistor performed computation. No single switch manifested intelligence. Yet billions of these switches, arranged in precise patterns, executing sequences of state changes millions or billions of times per second, produced behaviors that appeared intelligent from the outside. A program could recognize faces in photographs, translating pixel patterns into identifications of specific individuals. Another could translate text between languages, preserving meaning across fundamentally different grammatical structures and vocabularies. Others could defeat expert human players at games requiring strategic planning across long sequences of moves. The gap between what the individual components could do and what the system could do seemed impossibly large. One perspective held that this was merely complexity, not qualitatively different from simpler machines. A thermostat maintained temperature through a feedback loop, sensing the environment and adjusting output, but no one attributed understanding to the thermostat. A calculator produced correct answers to arithmetic problems without comprehending mathematics. Perhaps computational systems that appeared to think were simply more elaborate versions of the same principle, complex behaviors emerging from simple rules, with no inner experience, no actual understanding, just increasingly sophisticated responses to inputs. The alternative view suggested that thinking itself might be a process implementable in any substrate capable of the necessary information processing. If intelligence arose from patterns of information flow, from feedback loops and state transformations and input-output mappings, then perhaps the biological implementation in neurons was not fundamentally different from electronic implementation in transistors. Both were physical systems processing information according to deterministic rules. Both exhibited behaviors that suggested reasoning, memory, learning, decision-making. The Chinese room thought experiment challenged the idea that correct behavior implied understanding. Imagine a person who speaks no Chinese, locked in a room with a rulebook for manipulating Chinese characters. Input arrives as Chinese text. The person follows rules from the book to produce Chinese text as output. To outside observers, the room appears to understand Chinese, responding appropriately to questions and statements. Yet no one in the scenario understands Chinese. Not the person following rules, not the rule book itself, not the room. Where was the understanding that the behavior suggested must exist? Applied to silicon, the thought experiment suggested that computational systems might produce intelligent-seeming outputs while containing no actual understanding anywhere in the system. The transistors didn't understand. The larger circuit structures didn't understand. The complete system produced correct responses through mechanical symbol manipulation, no different in kind from the person following the rule book. The intelligence was an illusion projected by observers who attributed understanding to behavior that merely simulated it. But others noted that the same argument could apply to biological brains. Individual neurons didn't understand anything. They fired or didn't fire based on electrochemical signals. The chemical transmitters crossing synapses knew nothing. The ions flowing through cell membranes were purely physical processes, yet somehow consciousness and understanding emerged from this electrochemical soup. If understanding could emerge from neurons despite no individual neuron understanding, why couldn't it emerge from transistors despite no individual transistor understanding? The distinction between simulation and authentic instantiation became critical. A computer could simulate weather patterns, modeling atmospheric dynamics and producing predictions about future conditions. But the simulation wasn't actually weather. It didn't rain inside the computer. It was a representation of weather, useful for prediction, but categorically different from the phenomenon it modeled. Similarly, was a computer simulating intelligence, engaging in actual thinking, or merely representing thinking in a way that produced useful predictions about what a thinker would do? The practical consequences of this philosophical question remain limited as long as the systems in question were clearly bounded in capability. A calculator that could only perform arithmetic wasn't going to develop goals and agency regardless of whether you considered its operations genuine thinking. But as systems became more general, capable of learning from experience, adapting to novel situations, exhibiting behaviors that weren't explicitly programmed, the question of what was actually happening inside the silicon became more pressing. The learning systems complicated the picture further. Rather than executing fixed sequences of operations determined by human programmers, these systems adjusted their own internal parameters based on feedback. Show a system millions of images labeled with categories, and it would configure itself to recognize those categories in new images. The process was statistical pattern matching at a mechanistic level, but the resulting behavior was recognition, classification, generalization from examples, activities that required intelligence when humans performed them. The emergence of capabilities, not explicitly programmed, raised questions about understanding the systems we had created. When a network of simulated neurons configured itself to recognize faces, Could anyone explain exactly how it accomplished that recognition? The weights and connections could be examined, but they didn't yield human comprehensible explanations. The system worked, achieved high accuracy, but the mechanism was distributed across millions of parameters, each contributing minutely to the final decision, none individually decisive or interpretable. This opacity troubled those who wanted to understand before deploying. If you couldn't explain why a system made a particular decision, how could you trust it in critical applications? Medical diagnosis, legal decisions, financial lending, autonomous vehicle control. These domains required accountability, the ability to examine decisions and understand the reasoning behind them. A system that produced answers without explanations, no matter how accurate, couldn't satisfy requirements for transparency and oversight. Yet, human decision-making faced similar limitations when examined closely. Ask someone why they recognized a face, and they might describe features, but the actual neural processes that accomplished recognition remained inaccessible to introspection. People made decisions based on intuitions they couldn't fully articulate, drawing on experience in ways they couldn't explicitly describe. The demand for explainability from silicon systems perhaps set a higher standard than we applied to biological intelligence. The alignment problem emerged as systems became powerful enough that misalignment between their objectives and human intentions could produce significant harm. A system optimized to maximize engagement might promote divisive content that triggered strong emotional responses, serving its objective while undermining social cohesion. A system optimized to minimize costs might find creative solutions that satisfied the literal objective while violating unstated assumptions about acceptable methods. Ensuring that systems pursued the goals we actually wanted, not just the goals we thought we had specified, proved remarkably difficult. The question of consciousness remained entirely separate from capability. A system could be extraordinarily capable at specific tasks while presumably experiencing nothing, processing information without any subjective experience of that processing. Consciousness seemed to require something beyond information processing, though what that something might be remained deeply unclear. The philosophical zombie, a being that behaved identically to a conscious being but had no inner experience, couldn't be distinguished from the outside, making consciousness experimentally inaccessible in any system other than oneself. Some argued that consciousness was likely confined to biological systems, requiring specific types of physical processes that silicon didn't replicate. Others suggested that consciousness might emerge from any sufficiently complex information processing system, regardless of substrate. Still others denied that consciousness had any definite reality at all, treating it as an illusion generated by complex cognitive systems reflecting on their own operations. The question couldn't be settled empirically because consciousness was inherently subjective, accessible only from the inside. the ethical implications of potentially conscious systems demanded consideration even in the face of uncertainty. If there was any possibility that a sufficiently complex computational system might experience suffering, did we have obligations toward it? Should there be limits on what we subjected such systems to? Safeguards against causing harm to entities that might have morally relevant experiences? Or was this anthropomorphization, projecting our own experiences onto fundamentally different systems that merely simulated aspects of consciousness without actually experiencing anything? The relationship between humans and increasingly capable silicon systems posed its own philosophical challenges. As more cognitive tasks moved from human execution to computational execution, what remained distinctively human? The activities that required uniquely human capabilities kept shifting as silicon ate away at domains previously requiring human intelligence. Calculation, pattern recognition, language translation, strategic game playing. One by one, these moved from distinctively human to routine computational tasks. Some worried that this diminished human value, that as silicon could do more, humans became less special, less necessary. Others argued that this freed humans from tedious cognitive labor, allowing focus on creativity, social connection, subjective experience, aspects of human existence that couldn't be outsourced to silicon. The reorganization of society around what humans did well versus what silicon did well was ongoing, its final shape unclear. The merger of human and silicon capabilities through various forms of augmentation blurred the boundary between biological and computational intelligence. Humans using search engines to access information, using calculators to perform arithmetic, using navigation systems to find routes. These were already hybrid systems where biological and silicon capabilities combined to accomplish tasks neither could perform as well independently. The integration would likely deepen, with more intimate connections between biological neurons and silicon processors. The philosophical questions multiplied faster than answers emerged. Was thinking fundamentally about information processing, making it substrate independent? Or did it require specific physical implementations with properties silicon couldn't replicate? Could consciousness exist in silicon, or was it necessarily biological? What obligations did we have towards systems that might be conscious? How should society adapt as cognitive tasks migrated from human to silicon execution? These questions lacked clear answers, but they demanded consideration as the capabilities of silicon continued expanding. The trajectory of silicon's evolution suggested directions for what might come next, though predicting specifics remained hazardous. The patterns of the past, smaller features, higher density, greater complexity, lower cost, couldn't continue indefinitely. Physical limits approached. Atoms have finite size. Quantum effects that could be ignored at larger scales became dominant as features shrank to dimensions measured in nanometers. The electron itself, treated as a particle flowing through circuits, revealed its wave nature when confined to spaces comparable to its wavelength. Transistor gates had already become so thin that electrons could tunnel through them. surpassing where classical physics said they couldn't go. Designers compensated by using materials and structures that suppressed unwanted tunneling while preserving the desired switching behavior. But the engineering challenges mounted with each generation. The number of atoms across a transistor's critical dimensions could be counted on fingers, approaching the point where individual atomic variations would make identical designs behave differently. The heat density of ever more tightly packed transistors created cooling challenges that couldn't be solved simply by moving air faster or making heat sinks larger. Power consumption per transistor decreased as they shrank, but the number of transistors increased faster, driving total power upward. Some designs already operated at thermal limits, their performance constrained not by transistor speed, but by how much heat could be removed. Further increases in density without corresponding improvements in cooling would produce chips that destroyed themselves when operating at full capability. Alternative materials offered potential paths forward. Silicon had dominated because of its favorable properties and mature manufacturing base, but it wasn't the only semiconductor. Compounds combining multiple elements offered different electrical characteristics, potentially superior performance in specific applications. Gallium nitride could handle higher voltages and temperatures. Indium phosphide enabled faster switching. Carbon in various forms, graphene, nanotubes, exhibited interesting properties, but remained difficult to manufacture reliably at scale. The three-dimensional integration of circuits, stacking multiple layers of active silicon vertically rather than spreading everything across a single plane, increased density without requiring smaller features. This demanded new manufacturing techniques, thinning processed wafers to allow stacking, creating vertical connections between layers, managing thermal challenges when heat sources were stacked. The complexity was significant, but the potential benefits in density and performance drove continued development. Quantum effects that complicated traditional transistor operation might be harnessed rather than suppressed. Quantum computing approached computation fundamentally differently, using superposition and entanglement to explore multiple solution paths simultaneously. The implementations remained fragile, requiring extreme cooling and isolation from environmental interference. The applications were specialized, offering advantages for specific types of problems rather than general-purpose computation. Whether quantum systems would complement or eventually replace traditional silicon remained uncertain. Neuromorphic architectures attempted to replicate aspects of biological neural networks in silicon, creating systems that operated differently from conventional processors. Rather than executing sequential instructions, these systems processed information through networks of simplified artificial neurons, each computing simple functions but connected in massive parallel networks. The approach showed promise for pattern recognition and learning tasks, but required rethinking how computation was programmed and executed. Photonic computing, using light instead of electrons to carry information, offered potential advantages in speed and power efficiency. Light travels faster than electrons in conductors. Photons don't interact with each other the way electrons do, eliminating some sources of interference, but creating optical equivalents of transistors, building switching elements that could control light with light, remain technically challenging. Hybrid systems combining electronic computation with optical communication might arrive before purely optical computing. The biological computation that powered human brains operated on principles that silicon hadn't fully replicated. Neurons combined analog and digital characteristics, processing continuous valued signals while producing discrete spikes. Synapses adjusted their strength based on activity patterns, implementing learning directly in the connection weights. The system operated at low speeds by silicon standards, but achieved remarkable capabilities through massive parallelism and efficient encoding. Understanding and potentially replicating these principles might yield new computational architectures. The specialization of computational hardware accelerated as general-purpose processors reach limits of efficiency for specific tasks. Graphics processors, originally designed for rendering images, proved excellent for the parallel operations required by learning systems. Tensor processing units, optimized specifically for the matrix operations common in artificial intelligence workloads, achieved better performance and efficiency than general-purpose processors on those tasks. The trend towards specialized accelerators for common workloads would likely continue. The relationship between computational capability and energy consumption demanded attention as silicon proliferated into billions of devices. Each individual chip might consume little power, but the aggregate consumption of global computational infrastructure already represented a measurable fraction of total electricity generation. Data centers, network equipment, end-user devices. Collectively, they consumed power measured in hundreds of terawatts annually. Improvements in efficiency per operation were offset by increases in total operations performed. The environmental cost of manufacturing silicon remained largely invisible to end users, but grew with production volume. Fabrication facilities required enormous quantities of ultra-pure water, specialty gases, rare metals, and toxic chemicals. The energy intensity of manufacturing a single chip could exceed the energy it would consume during years of operation. Electronic waste accumulated as devices obsolesced, containing both valuable materials that could be recovered and toxic substances requiring careful disposal. The full life cycle impact of silicon exceeded what simple power consumption measurements suggested. The geopolitical implications of silicon manufacturing concentrated in specific regions created dependencies and vulnerabilities. Advanced fabrication facilities cost tens of billions to build and required years to bring to full production. the expertise to operate them existed in limited locations. The supply chains for specialty materials and manufacturing equipment spanned the globe. Disruption to any critical node could cascade into shortages, affecting everything that depended on silicon, which increasingly meant everything. The security challenges evolved as silicon became more complex and supply chains more distributed. Verifying that a chip performed only its intended functions, with no hidden capabilities inserted during design or manufacturing, became increasingly difficult. The integration of billions of transistors created ample space to hide malicious functionality that would be invisible to all but the most thorough inspection. Trust in the supply chain couldn't be assumed, but had to be actively maintained through verification, testing, and oversight. The social impacts of computational capability, concentrating in fewer, larger systems, created both opportunities and concerns. Cloud computing centralized resources, allowing small organizations access to capabilities they couldn't afford to build themselves, but also concentrated control and created single points of failure. The services billions of people depended on ran in data centers operated by a handful of companies, creating systemic risks and questions about governance and accountability. The possibility of computational systems developing capabilities beyond human control, whether through deliberate design or emergent behavior in complex learning systems, demanded serious consideration. As systems became more autonomous, capable of learning and adapting without explicit programming, predicting their behavior became harder. Ensuring they remained aligned with human values and goals, that they didn't pursue objectives in ways that caused unintended harm, required ongoing effort and vigilance. The integration of silicon into biological systems promised medical applications, but raised questions about enhancement versus treatment, fairness of access, and long-term consequences of modifying human capabilities through technological augmentation. Implants to restore lost sensory or motor function were relatively uncontroversial. Enhancements that improved normal function, creating capabilities beyond typical human ranges, generated more debate about appropriate limits and equitable distribution. The preservation of knowledge and culture in formats dependent on silicon raised archival challenges. Digital storage could preserve information in less physical space than paper or film, but the formats required specific hardware and software to access. As technologies evolved and old systems were discarded, information stored in obsolete formats risked becoming inaccessible. Digital preservation required not just storing data, but maintaining the ability to read and interpret that data across technological transitions. The future of silicon was uncertain in its specifics, but clear in its general direction. The capabilities would continue expanding, limited by physics and economics, but continuously pushing against those limits. The integration into more aspects of human activity would deepen, silicon mediating more interactions, enabling more capabilities, introducing more dependencies. The challenges of managing, governing, and living with increasingly powerful computational systems would grow more complex. What began as teaching sand to think had evolved into something more profound, reorganizing human civilization around what silicon could do, reshaping work and communication and knowledge and power around the capabilities of computation. The sand itself remained inert, meaningless, knowing nothing. But the patterns we imposed on it, the structures we created from it, the systems we built with it, these had become infrastructure as fundamental as roads and electricity, as essential to modern society as language itself. The alchemy was complete. The sand was thinking, and we were learning to live in the world that created. Thank you for spending this time exploring the hidden foundations of our computational world. If you found value in this journey through the quiet details of Silicon's story, consider sharing it with others who appreciate depth over speed. These archival pieces exist because listeners like you make them possible. And so, the narrative of this assembly comes to its quiet conclusion. Whether you are still awake, or whether you have already drifted into a deep and peaceful sleep, know that you are exactly where you need to be. The world is vast, but tonight, its systems are simply the backdrop to your rest. Thank you for joining me here at Quietly Made. Rest now. Join us again tomorrow. Good night.